We are going to start our problem with a square with the area 16. Then we're going to stack another identical 3 squares just as shown in the sketch. Now we're going to circumscribe the circle around those 4 squares in such a way that it will touch the bottom left corner of our left square and the top right and bottom right corner of our right square as shown on the sketch. The question is, can we somehow calculate the area of this red circle? This viral problem was presented to me by one of my subscribers, Joshua. So Joshua wanted me to do this problem without using analytical geometry or trigonometry. So this is exactly what I'm going to do in this video. But, of course, you guys can pause the video right now and try to do this problem in whatever way you like and then come back and check the solution. Alright, so let's solve this one. Like I said earlier, I'm going to use 2 different geometry methods, and for the first method I will use the method which I think is the easiest one. But is it? Well, you guys will be the judge of that. So we will start with the fact that the area of our small square is equal to 16. Of course, since we know that the area of the square is equal to the side squared, we can easily find that the side of our square is equal to 4, so we're going to substitute those values in. Next, I'm going to label the intersection points with the circle as A, B, and C. And I will also label the center of our circle as O. Then I'm going to use one really interesting property of the circular chord, which states that the perpendicular to a chord drawn from the center of a circle bisects this chord. So if we notice that the line BC actually represents the chord of our circle, we can label the center of this chord as D, which is going to divide the line BC into 2 segments with the length of 2. Then, if we pull the perpendicular bisector through the point D, this line will have to go to the center of our circle O because of the previously mentioned property of a circle. Alright, so now I'm just going to pull the radius of a circle from point O to point B, and I will label this radius as R. Next, you can notice this really nice right triangle ODB. So we can use the Pythagorean theorem. We can say that the leg OD square is equal to the hypotenuse OB square minus the leg BD square. And we're going to substitute our values, work through this, and get that OD is equal to square root of R squared minus 4. Next, I'm going to pull the horizontal line from the point A, and I'm going to pull another vertical line from the point D, and the intersection of those 2 lines I will label as E. Now, if we put another square in the gap between our squares, you can notice that the line AE will have the length of 4 sides of the square, which is of course equal to 16. Furthermore, we can notice that the line CE is actually the side of the square, so it must have the length of 4. This means that the line DE will have the total length of 2 plus 4, which is equal to 6. Now we will slide the line DE to the left up until the center of our circle O, and we will label the intersection of this new line with the line AE as F. Next, let's clear our image and notice the line OD. You can see that we can get the line AF as the difference between the line AE and OD. So the line AF will have the length of 16 minus square root of R squared minus 4. Alright, so now let's go back and finally pull the radius from the point O to the point A. And you can notice this really nice right triangle AFO. So again, we're going to use the Pythagorean theorem. We can say that the hypotenuse AO squared is equal to the sum of the legs AF squared and FO squared. Of course, we're going to substitute our values and put everything to the square. Of course, we're going to use the square of binomial to expand, and we're going to get the following. Here we can cancel r squared on the both sides of the equation and simplify. Then we can divide everything with 32, then put everything to the square, and we will finally get that the radius squared is equal to 85. Now it's pretty easy for us to find the area of the red circle, as the area is equal to r squared pi or pi r squared, whatever you like. So we're just going to substitute the value of r squared that we got before, and we're going to get that the area of our red circle is equal to 85 pi squared units, and this is our solution. Alright, so now I'm going to show you another way to solve this problem without using analytical geometry or trigonometry. This option will be a little bit more complicated, but it will be just as fun. So we're going to start our method the same way as the previous one. We are first going to find the side of the square to be equal to 4. Then I'm going to label the intersection points with the circle the same way as before, so A, B, and C. Now this time I will pull the line from point A to point B, and I will label the upper right corner of our upper square as D. Now I will pull another line from A to D, and we can notice that this line actually goes through the diagonals of our three squares. Then I will pull another line from point D to point B. And if we construct another square there, you can see that the line DB is also equal to the diagonal of the square. Now, in this way, we have formed this really nice triangle ABD. But this is also the right triangle, since the lines AD and DB are both diagonals of the squares with the same size. Now we know that the diagonal of the square is equal to the side times square root of 2. In our case, this diagonal will be equal to 4 square root of 2. So now we're first going to substitute this value for the line AD. Since this line is equal to 3 diagonals, this is 3 times 4 square root of 2, which means that this length is 12 square root of 2, and we're going to substitute the value for the line DB for 4 square root of 2. Now, of course, we will use the Pythagorean theorem to find the line AB. So the hypotenuse AB squared is equal to the AD squared plus DB squared. We're going to substitute our values, put everything to the square, and finally get that AB is equal to square root of 320, which we can simplify to 8 square root of 5. Alright, so now we will go back to our previous sketch. And we're going to pull the line from the point A to the point C. Then we're going to pull the horizontal line from the point A and a vertical line from the point C so that those two lines intersect at the point E. Now you can see that we have again formed a really nice right triangle AEC. So as in the previous method, if we put a square in the center to fill the gap, you can see that the line AE will have the length of 4 sides of the square, which is equal to 16, and the line CE is equal to the side of the square, so it must have the length of 4. Now let's find the length of the line AC by again using the Pythagorean theorem on our triangle. We can substitute the values, get everything to the square, and finally get that the line AC is equal to square root of 272, which we can simplify to be 4 square root of 17. And now, if we take a look at the line BC, this line will also represent the side of the square, so it must have the length of 4. Now you can notice that we have formed this really nice triangle ABC. And furthermore, if you take a look at our circle, whose radius I'm going to label as R, this circle will actually be the circumscribed circle around our triangle. So now we're going to use one really interesting formula for the area of the triangle in terms of circumradius. This formula states that the area of any triangle is equal to the product of its sides divided with 4 times the value of circumradius. So this formula is actually perfect for us because we can find the radius of our circle. But, as you already noticed, we do not have the area of the triangle, and we're going to use another interesting formula, which is called the Heron's formula. With this formula, we can find the area of the triangle by only using the sides of the triangle, where A, B, and C are, of course, sides of the triangle, and S represents the semi-perimeter, which we can calculate easily. First, we're going to do that by putting our sides A, B, and C, and when we simplify with 2, we will get our semi-perimeter. So, since this is going to become a little bit messy right now, I'm going to just clear the image and only take the values for S, A, B, and C. Then I'm going to put those values into the Heron's formula, and when we do that, we will get this really huge sausage of the expression. Now we're going to just simplify the factors a little bit, and we're going to work through this. Now, of course, I'm not just going to calculate the area, I'm going to take you through the whole process to see how we got to this solution. So please, if you're a newcomer to mathematics, do not get intimidated by this. We can easily solve this by using a few techniques. First, we're going to rearrange the terms inside our brackets like this. Then, in order to solve this, we're going to use a little trick. We're going to use the reverse formula for the difference of squares. And let's notice that in our first 2 brackets, we have actually the values a plus b and a minus b. Of course, I have color graded this so that you can follow this a little bit easier. Now, this is exactly what we need in order to use the formula for the difference of squares. And we have the same thing in our other 2 brackets. We can again divide those factors and get the same thing for which we can use the same formula for difference of squares. Now, if we apply this formula, we can simplify this to get the following. Here we will put everything to the square and expand by using the square of binomial. Then we can simplify this to get that the area of our triangle is equal to the following. Now here you can easily see that we again have the numbers which can easily be translated to the same formula for the difference of squares. So we're going to do just that. Now we're going to put everything to the square, and we're going to get that the area of our triangle is equal to square root of 1024, which means that the area is equal to 32. So let's go back to our previous sketch and let's just replace this value into our formula for the radius, and let's also replace the values for A, B, and C. Now we can simplify this by cancelling 4s and then cancel the 4 times 8 with 32, and we will get that the radius of our circle is equal to square root of 85. Now, again, it's pretty simple to find the area of this circle as r squared pi. We're going to substitute the value of r, and again we will get that the area of our circle is equal to 85 pi squared units, and this is our solution. Well, which method do you guys prefer, method number 1 or method number 2? Or maybe you found another more easier method to do this. If you did, please write it down in the comment section below. I always love to see the diversity of solving the mathematical problems. And of course, if you enjoyed this video as much as I did making it, please leave a like and consider subscribing to the channel for more content. And until next time, see you all and take care.